Hey there, guys. Thanks for joining me tonight on this live broadcast for the second semester final review. Before we get going and I start answering the questions that were provided on the Google Doc, which is how I'm going to run the whole review, I do want to go over just a few things for you all tonight as reminders for your final exam. First and foremost, please make sure you bring your textbook with you, as it's super important that you turn that in because it's like $80, and if you don't turn it in, we charge you for it. So make sure you have your textbook with you. Do not forget to have your excuse me. Do not forget to have your cheat sheet handy, as I know many of you are relying on that to help you on the exam. So please make sure you have that with you as well. Things that you get on your cheat sheet, things you get on the exam, remember, are just the activity series from the last test. So the list of the elements from most reactive to least reactive, and then any electronegativity number that you would need. That's also what you would have handy for you on the actual exam itself. So those are the only two things you get. Otherwise, you guys are going to be providing the rest of the stuff. So that's what you get on the exam. I know you're all going to do awesome. So if you have any questions between this broadcast and your final, you can go ahead and shoot me an email. I am going to go to bed after this, though, so I may not get back to you until sometime tomorrow. But let's go ahead and let's get started. Like I said in class, I'm going to use the doc that you guys made to answer questions, and I've turned them into a Word doc that I'm going to write my answers on, that I will save and post on my website as well. So like I said, happy studying, and we're going to go ahead and get started. The very first question that I got was, oh, that is not a 9 that I'm typing in right now. Was, do we get the mole map? No, you do not get the mole map. You must provide your own mole map. So make sure that you write that down on your cheat sheet. So no, you do not get the mole map. And we're going to go ahead and we're going to screen share. I think this is the one I want. All right. So let's go ahead and start getting questions other than do I get the mole map? Question number 2. How are particles assumed not to attract or repel each other that causes particles to collide? That's one of the assumptions of KMT. So let's go ahead and let's run through the KMT itself again. I'm just going to minimize this for now. Sorry, I know you guys can't see anything right now. That's what I want to have. So answered this guy here. Done. On to the next. So how are particles assumed not to attract or nor repel each other if the pressure causes particles to collide? So it's really not pressure that's causing particles to collide. What it is the actual motion of the particles themselves. So if I was to go ahead and draw just kind of a container, when we have gas trapped in a container, those particles are in constant random motion. So they are randomly moving and colliding at their own pace. It doesn't matter if our container is big or if our container is small, those particles are still colliding. What this part means here, that they do not attract nor repel each other, is that there's no sort of force between these particles causing them to come to each other to form a collision. So it's kind of like these guys are just a bunch of spheres in their own space doing their own thing, and the only time they're going to change direction is if they hit a particle that is in their way. So there's no sort of attractive force from this guy saying, hey, you guy down here, you come by me and you attract with me and we make a collision together. This just says that they're in constant random motion, and the only time they are going to collide is when they happen to run into each other. So if you remember the video we showed you in chapter 17 with the nose face, arm face guys, it wasn't like there was a guy across the street saying, hey, lady, come here and hit me. They just randomly ran into each other in the street, and that's what caused the transfer to occur. So that's what this piece here means, is that we just assume that there's no attraction or repelling, because it helps us understand how gases behave a little bit more. So I hope that helped you out with that one. Our next question is all about balloons inflating. So how would a balloon inflate from being taken inside the house to the outside in the middle of January, and how does KMT relate to that? So if we think about just gases in general, if I think about a balloon inside the house, this question is actually not correct. My balloon is not going to inflate when I take it outside. My balloon's going to deflate. So this is wrong. This should actually say deflate. Oh, sorry, apparently I'm being too loud. I need to talk quieter. Is she moving? Oh, sorry, I'm waking the baby up. I need to talk quieter. I hope you guys can still hear me. All right, so why would this balloon deflate from being taken inside a house in the middle of January, and how does KMT relate to this? So if we think about this balloon that's in my house is a nice balmy 70 degrees because I get cold all the time. So what that means is my particles are moving at an average kinetic energy that's going to bounce off the side of these walls at a speed determined by 70 degrees Celsius. So if I take this outside in January, where we know it's Chicago, so maybe it's, like negative 10 degrees Celsius outside, that means my particle movement is going to decrease from 70 degrees Celsius to negative 10 degrees Celsius. So I'm going to see a drop in the kinetic energy of my gas particles. So because my gas particles aren't moving as rapidly as they are in this balloon, my balloon size is actually going to get a lot smaller because we're no longer having enough collisions to increase the volume of the balloon. So our kinetic energy drops, which means we're going to drop the number of collisions. And because the number of collisions is dropping, that means the pressure inside our balloon drops, which means that our volume is going to drop. And the main reason our volume is dropping is because since our pressure inside here is decreasing, the air that's on the outside of the balloon now can push in at all directions and make that balloon a much smaller volume. So because we're moving slower, we're having less collisions, which is exerting less pressure, the air outside is going to squeeze that balloon into a smaller space. Now, how KMT relates to this is we assume that gases are in constant random motion that's determined by the temperature. So since we're dropping the temperature, we're dropping the speed, which is going to drop the volume. So I hope that this has helped with that question. On to the next. So someone asked, can you go over which problem uses which gas law equation? And will you tell us which gas law we're using, or do we have to figure it out ourselves? You guys are definitely 100% going to have to figure it out yourselves for this one. So there is no like, hey, using Boyle's law, do this math. Everything you're going to do is going to be based off of you guys being able to understand. I'm going to go ahead and put me back here because I'm not. You guys are going to have to be able to understand which gas law is using which equation. So my biggest hint for you guys on that one is as you're reading a problem, go through and underline the different variables you have, and that's going to help lead you to which gas law you need. So for example, we know Boyle's is P1 V1 equals P2 V2. So if I'm doing a Boyle's law equation, as I'm reading the problem, I would either see two pressures or two volumes in the actual equation itself. And then I would only have one of the other variable. So I would make sure that you are just going through the problems and reading an underline and assigning a variable, either pressure, volume, or temperature, to what you're reading in the problem. So if you're seeing conditions changing, you know it's either going to be a Boyle's, a Charles, a Gay-Lussac's, or a combined, because those all have two sets of variables. They all start out with something in the ones, so either P1 V1, P1 V1, V1 T1, T1 P1, or PV and TL1. I know that's really confusing. But they'll start with one set of conditions and go to a second set, where something like Pivnert only will have one of each variable. So if you only see one pressure, one volume, one mole, or one temperature, then you would definitely be using a Pivnert equation there. With Pivnert specifically, we will give you that R number. You don't have to memorize any of those. Those will be provided to you. All right, so let's go ahead and let's go back to the doc. Our next question that we have asks about, can we do an example of a problem that has the entire mole map? And then how do you go from volume to moles on the mole map when you're using Pivnert? So I'm just going to make up a problem. I'm not promising it's going to be amazing. If you think about the mole map itself, I'm going to try and draw a little just mini guy in here for you up here in this corner. So when I'm going between volume and moles, we know there's two arrows we can use. So if this is mole 1, mole 2, volume 1, and volume 2, we know if I'm at STP, I get to use the fast lane, which is molar volume. We know if I'm not at STP, I have to use the Sloan lane, which is PivNert. So how do I do a problem like this? So let's say I had the following combustion reaction. So we're gonna make some carbon dioxide gas because I can come up with a combustion equation real quickly. So CH4 plus O2 gives you CO2 plus H2O. Let's go ahead and balance. So I need a 2 here. I need a 2 here. Okay, so let's say I have, so if I combust 15 grams of CH4 at 25 degrees Celsius and 1.5 atmosphere, how many liters of CO2 do I make? So if we read this problem, what we've got going on is we've got 15 grams of CH4, so I'm starting with this, and I want to know how many liters of CO2 I can make. When I'm looking for those STP conditions, remember STP means you're 0 degrees Celsius and 1 atmosphere. So if I look at the problem, I've got 25 degrees Celsius and 1.5 atmosphere, so I'm not at STP, so I cannot use my fast track. I have to use my slow track. So because I'm starting at grams and I'm ending at volume, I have to go from grams to moles to moles to volume. But I'm going to have to kick out and use PivNert because I'm not at STP. So what would a problem like that look like math-wise? So when I'm going from grams and I want to get to mole 1, the first thing I have to do is I have to use my molar mass. So I know 15 grams of CH4 roughly weighs 16 grams. If I wasn't smart, I would show 16, whatever. That's roughly 1 mole of CH4. So when I do this first step, what it's doing is taking me from mass 1 to mole 1 because my grams cancel. So I'm now in moles of CH4, so I'm in this box. Because I want to get to liters of CO2, I have to get to mole 2 second. So this is where my mole ratio comes into play. If I look at my problem, my coefficient is nothing, so it's 1 in front of CH4. My coefficient in front of CO2 is nothing as well, so it's just 1, so my mole ratio is 1 to 1. So for every 1 mole of CH4, I get 1 mole of carbon dioxide. And this is where I have to stop my work because since I'm not at STP, I have to stop here and I'm going to kick out into PivNert to do my math. So on my calculator, I'm just going to do 15 divided by 16. And because I've got 2 sig figs, this gets me 0.94 moles of CO2. So I'm going to go ahead and I'm going to use PivNert to finish my problem up. So because I was at moles and I want to solve for volume, I'm solving for the V in PivNert. My P comes from my problem, which is 1.5 atmospheres. Oops. I'm solving for volume. The moles is what I just solved for, which is 0.94. The R number will give you every single time, which is 0.08206. And then remember, anytime we're doing temperature in PivNert, it always has to be in Kelvin. So I'm going to add 273 to my temperature to get myself 298 Kelvin of my temperature. So now I would just do algebra. I would do my moles times my R times my temperature. And then I would divide by my atmospheres. And that gets me to sig figs 15, and my volume will be liters when I'm done with that. So that's an example of a mole map problem that has to deal with PivNert. Now, how you know what part of PivNert you're solving for all depends on which way you're going on this arrow. So in this case, I was going from moles to volume, which is how I knew I was solving for volume. In the event I was starting in volume and wanted to go to moles, that meant that I would have to go with moles second, and I would solve for moles. So my problem, I would see a pressure, I would see a volume, and I would see a temperature. So if we just do a quick example of something like this, I'm going to kick it down here. A quick example of something like that might read, so if I do the same equation here, I have 2 moles of O2 I'm assuming the same things at 25 degrees Celsius and 1.5 atmospheres. How many grams of CH4 do I have? So if I look at this time, because I know how many, I don't have 2 moles. I want 2 liters. So if I look at this time, because I know here is a volume, here is a temperature, that's a degree Celsius, even though it's terribly written. And this is a pressure. I know I'm starting with pig inert first. And I'm going to do the mole map second. So my pressure would be my 1.5 atmospheres. My volume would be my 2 liters. In this case, I don't know my moles. And again, I'm at the same 298 Kelvin. So this time I would solve for moles. So I would do my 1.5 times my 2. That's all liters, by the way, which gets me 3. And I would divide it by my 0.08206 times 298. And that gets me 0.12 moles of O2. So now I'm here in my mole map. I'm at mole 1. I want to get to grams, so I'm going to go to mole 2 and then to grams this time. So I'm just working backwards on my mole map. So if I look at my coefficient now, I'm using my mole ratio. So 2 moles of O2, because I've got a 2 in front of O2 here in this equation, and I'm solving for CH4. So I need 2 moles of O2 to react with every 1 mole of CH4. And then we already know that 1 mole of CH4 is roughly 16 grams. So now I would do my 0.12 times 16 divided by 2 in my calculator to get me 0.96 grams of CH4. So this tells me that at 25 degrees Celsius and 1 atmosphere, if I want to fill 2 liters of volume with O2, I would need 0.96 grams of CH4 to react with it. So that's our mole map stuff. I hope that this was helpful for you guys. And now we're going to move on to chapter 14, which is IMF and state changes. So will you get the VSEPR chart? Nope. No VSEPR chart for you guys. You do not get a VSEPR chart. So that is definitely something that you want to put on your cheat sheet. And remember, it must be handwritten. So you do have to handwrite that VSEPR chart in, but you guys can probably condense it down to a lot smaller chart than what I've done anyways. So you do not get this. You must write it yourself. So no VSEPR for you. No. All right, can you go over the drawing of Lewis dot to VSEPR? Absolutely. I'm just going to pull a quick VSEPR chart in here real quick from my website. Just give me a second. I should have had this already ready, but you know, the struggle is real with Mrs. Etnire. We're all used to it. There we go. All right, so this is your VSEPR chart. This is something that that came in really, really large. Let's go ahead and make that smaller. You guys are enjoying this as much as I am at home. Probably not, but you know, I love chemistry. You guys hopefully love me. So there we go. All right, now let's do VSEPR charts. This is definitely what you want to write on your test. You definitely want to go ahead and write this. Remember when we talk about how to use this chart, we don't want to think of this as number of electron pairs. We want to think of this as sides of the atom. So how many sides of our atom are taken up with. And remember, we don't look at the bond column up here. We only look at the bond column when we get to these guys down here at the bottom. So I'll do a couple of examples for y'all so we can go ahead and remember how to use this VSEPR chart. So how to draw a Lewis dot structure. If I have something like, let's go with an easy one. Let's go with water. You can either do the picture method or the math method. I'm going to do all my picture method style just because I think it's easier. So when you do the picture method, remember H's cannot go in the middle. So we're going to put O in the middle and we're going to give it its number of dots. Because it's in the 6th column, that means it gets 6 dots. So remember, we start by giving one side a dot and then we can go back and pair. So this will be my 6 dots for the O. H's are in column 1, so they each get 1 dot. And then we play connect the dots. So here and here would be where I connect my dots. My O is octet happy because it's got 2, 4, 6, 8 electrons, and my H's are duet happy because they both only want 2 electrons, because remember, H is an exception to the rule. So now I can go ahead and I can apply my VSEPR chart to it. So the first thing I want to do is I want to count how many sides are taken up on this O. So this is side 1, this is side 2, this is side 3, and this is side 4. So I have 4 sides taken up on my O. So I follow myself to my sides, and I see that I've got 4 options in the sides area. So this is where the number of bonds is going to come into play. I only have 2 bonds. So that means I am in this row here, where I've got 4 sides and 2 bonds. So my VSEPR is going to be what we call the bent shape. So how I would draw that is I would put my O in the middle, and then I would go ahead and I would drop my H's down. I'm just going to copy the picture exactly like I see it in the chart. Now remember, I say you don't have to draw those bubbles there. I just go ahead and I put my lone pairs on the top like that. So this would be the VSEPR for water. Let's do something a little bit more complex. Let's look at carbon dioxide. So if I'm doing my Lewis, my C is going to go in the middle, and he's going to get 4 dots. And then my O's are going to go on the outsides, and they're going to get 6 dots. And this time I'm going to leave my lone pairs on the top and the bottom. So I'm going to play connect the dots to make sure everyone's happy. So I can connect these dots. I can connect these dots. I can connect these dots. And I can connect these dots. And when I'm done counting, we've got 2, 4, 6, 8 around the O, 2, 4, 6, 8 around the C, and 2, 4, 6, 8 around the O. So I like to rewrite this so it's not so crazy to see. So it looks like this. So that's our Lewis. So now I'm going to go ahead and I'm going to look at the VSEPR. This is side 1. This is side 2. So I now am in this top row where only 2 sides are taken up. So that means it's going to be linear. So it's going to look exactly the same. I draw my double bonds on the outside, and I draw my O's on the outside. And I now have my linear VSEPR shape. So I hope that's helped as a quick review about how to go between Lewis dot and VSEPR. So let's go ahead and let's go down here. Next question. Oh, where's my cursor? There it is. How can you determine molecular polarity, and how can you use electronegativity to determine polarity? So on your test tomorrow, you will get all the electronegativity, or whether it's tomorrow, the next day, or whatever, it doesn't really matter when your test is. You will get all the electronegativity numbers that you get. Header, sorry, come on, look up. All right, you will get all the electronegativity numbers that you need. So this is not something that you need to memorize. This is something that will be provided for you on your exam. Excuse me. So you guys do not need to memorize that. Okay, that's just simply something that will be provided for you. You just have to know how to use them. So how you use the Lewis dot structures, or sorry, how you use the electronegativity numbers is based off a little bit of a rule. So when we're looking at bond polarity, for a bond to be polar, that means it needs an electronegativity difference greater than 0.5. So 0.5 or higher equals polar bonds. Oh gosh. Nonpolar means it's going to have a difference in electronegativity that's 0 to 0.4. So let's go ahead and let's use these 2 examples from above. So I have water, which was this guy here. And I had carbon dioxide, which was this guy here. So when I look up the numbers of the electronegativity, which would be given to you guys, you don't have to memorize these. O is 3.5, H is 2.1, and C is 2.5. O might be 3.0. I can't remember. I think O is going to be 3.0. We're going to go with O is 3.0. No, it's 3.5. It's 3.5. Okay, so how we figure out if a bond is polar or not, what we do is we subtract the two numbers. So here, the difference between 3.5 and 2.1 is 1.4, so that means these are polar bonds. And remember, we use arrows to point at the person with the bigger electronegativity because these guys are playing tug of war with those electrons. So remember we talked about if the difference is greater, it's like a sumo player playing tug of war against toddlers. He's going to be able to pull the electrons a lot closer to his person. If we do the same thing over here, C is 2.5. O is 3.5, which is a difference of 1. So again, we have polar bonds. So in this case, we still point our arrows at the O because that's got the larger electronegativity, meaning it's going to pull the electrons closer to its nucleus. So we have polar bonds in both of these molecules. Now, how do we determine if the molecule is polar? Remember we talked about it being like in a tug of war, will you see the atom move? Because if the atom moves, then it means you have a polar molecule. If the atom doesn't move, it means you have a nonpolar molecule. So if you look at this example over here, the C is trapped in the middle of two O's pulling electrons in opposite directions. So because this C is being pulled to the right and pulled to the left equally, it's not going to move anywhere. So even though it has polar bonds, this is a nonpolar molecule. If we look at this guy water here, because the H's are being pulled up towards the O, there's nothing pulling opposite them to keep them in place. These H's are going to move, so this would be a polar molecule. Now the chemistry behind what's happening is because as these electrons are being pulled up, they're spending more time around the oxygen's nucleus than they are the hydrogen's. So this portion of the atom is taking on a slightly negative charge, but this portion of the atom is taking on a slightly positive charge. So you end up with 1/2 negative and 1/2 positive, which is by definition a polar molecule. Over here in this example, because the electrons are all being pulled out in opposite directions, you don't get that. You don't get that 1/2 negative, 1/2 positive. So before you can determine if a molecule is polar, you first have to figure out, are the bonds polar based on the electronegativity difference? So this is what happens first. Then once you've done that, you want to ask yourself by putting in polar arrows, will the molecule move? If the molecules will move, it means you're polar. If the molecules won't move, it means you're nonpolar. All right, now I'm going to be honest. This next question, I'm not 100% sure what's asking me, so I'm going to do my best to answer it. So if you're the person that wrote this, I'm sorry. I hope that I am answering this correctly. If I'm not, please shoot me a follow-up email, and I will try and help you out later via email. So what are the differences between the bonds? I'm not certain if you're asking me about ionic covalent or if you're asking me about intermolecular forces. So I'm going to answer ionic covalent because I'm going to answer intermolecular forces the next question. So difference between bonds. An ionic bond is where you have a metal bonded to a nonmetal. And as we learned, that's not at all how you spell metal and nonmetal. I'm going to try and write that a little bit neater and with the right terminology. As we learned in the redox chapter, the metal is going to lose electrons to the nonmetal, so these are transferring electrons. You end up with a positive ion and a negative ion, and that's what attracts each other in the bond. It's the attraction between the positive and negative. In a covalent bond, you have two nonmetals. So what they're going to do is they're going to share electrons, so you don't see the positive and negative. What you see instead are these lines, and those lines indicate the sharing of one or more electrons between the two atoms. So that's the difference between ionic and covalent. I hope that helped you out. I hope that was the right question. If not, I am going to talk about intermolecular forces here in the next part. So this next one talks about intermolecular forces in terms of melting point and boiling point, and how you can tell what has the highest melting point based off of the intermolecular forces. So first thing we want to do is we want to do a quick review of the intermolecular forces. Remember, London dispersion are going to be for things that are non-polar. So an example of that would be like carbon dioxide here. So carbon dioxide molecules are going to be held together by London dispersion forces. So when you have a chunk of dry ice, it's those London dispersion forces that are going to be holding them together. And these are the weakest. The next type of force we have our dipole-dipole, which I'm going to write with DP. Remember, a dipole-dipole is going to be the attraction between two polar molecules. So if we look at HCl, for example, HCl is a polar molecule where the Cl is becoming kind of negative and the H is becoming kind of positive. And we first figure out that, like I explained above, where we do the difference in electronegativity, and we can see that this is a polar molecule and the electron is being pulled towards the chlorine because it has the larger electronegativity of the two. So if I have a second HCl molecule, this side is kind of positive, this side is kind of negative, my dipole-dipole is going to be the attraction between that negative side and that positive side. So this is going to be what holds the HCl molecules together when they're in a liquid state of matter. So London dispersion forces are the weakest. Your dipole-dipole are going to be kind of in the middle in terms of strength. So they're stronger than London dispersion, but they're not stronger than hydrogen bonding. So if we were kind of talking about which one would have the highest melting point, if we had something that had London dispersion compared to something with dipole-dipole, your London dispersion would have the higher melting point because their forces are stronger to break than the London dispersion. So the easier you are to break, the less energy you need to melt, the lower your melting point. The stronger your force, the more energy you need to break, the higher your melting point. Our last example of dispersion forces, last example of intermolecular forces is going to be your H bonds. Remember, these are only going to be when H is stuck to or bonded to an O, F, or N. So if we think about water, we just drew this guy up here. Oh my gosh, Anna, you're struggling right now. We know this side's kind of negative. We know the H's are kind of positive. So if I bring in another water molecule, we have a super strong attraction that's going to occur between the negative of one water molecule and the positive of the second. So this is going to be the strongest. So these are going to take the most energy to break. They're going to be the hardest to overcome. So this would have the highest melting point of all. So on your quiz, or sorry, not your quiz, on your final tomorrow, if I ask you, hey, which of these has the highest melting point, what you want to do is you want to figure out what type of force does it have. Does it do London dispersion? Does it do dipole-dipole? Or does it do H bonds? So first, you're going to have to figure out what type of intermolecular force it does by looking at the VSEPR structure. Then you can use that to figure out how it would relate to melting point. So Lewis Don VSEPR first to figure out forces. Second, use that to figure out, is it the weakest, does it have the most strength, or is it the strongest? Strongest, hardest to break, highest melting point, highest boiling point. Weakest, easiest to break, lowest melting point, lowest boiling point. And that's intermolecular forces. On to chapter 15. Someone in this chapter also asked, how do you tell the difference between ionic and polar? Ionic and polar. That goes down to what we just kind of talked about above. An ionic compound is going to have a metal and a nonmetal. So that's the big thing you're going to look for is, excuse me, something ionic is going to have a metal and a nonmetal. Something polar and small ionic, right? That looks wrong. A polar is going to be 2 nonmetals. And then you determine polar using VSEPR chart. If I give you, for example, something is soluble in water, you'd want to look at the compound. If it has a metal in it, it's got to be an ionic compound. If it doesn't have a metal in it, it's got to be a polar compound. So that's the big thing, is you want to look for the metal. The metal is the muy importante part here. So that's going to be what would kind of distinguish a metal from a non-metal. Where did my pen go? Bring me my pens back. There we go. Okay. All right, so now I got a bunch of questions about review questions 19 through 24. So I'm just going to kind of run through these real quick. This one, I believe, is 19. This one is 20. Okay, so I'm going to run through these real quick just to help out the person who asked about these on the packet. All right, so how do you know what equations to use? So if we look here, because this guy has a big M on the back, that's going to tell me that I'm going to use my molarity equation. So you can use your units to help you out a ton here. So this guy would have to be molarity. And so if we look at the molarity is equal to moles over liters. So if I read this problem, it says a 3.5 molar KNO3 solution contains 3.5 moles of KNO3 dissolved in what? So if I look at my options, because it tells me it's 3.5 molar, that means I've got 3.5 moles for every 1 liter of solution. And it's really, really important that you know molarity is liters of solution, not solvent. So this tells you how many liters of total solution you have. Our next one, the number of moles of solute in 0.2 mils of a 0.5 molar solution is. Again, we're going to use this exact same equation because we see that big M in the back. So I'd set this problem up as you have your molarity is 0.500. So you would put X on top because you don't know moles. And because it's per liter, we have to take this number and divide by 1,000. So this would be 0.200 liters on the bottom. So I just do 0.5 times 0.2, and that gets you your X is going to be 0.100 moles, which is how we get to this answer D down here. So my guess is if you're getting B, it's because you're not dividing by 1,000. Number 21 says of 500 milliliter solution of 1.5 NaCl solution contains, because these are all grams, when we're done with this equation, what we have to do is we have to do molar mass to go from grams to moles. So if we run through this problem here, you have that same 0.15 big molar equals X. And again, we have to divide this by 1,000. So it's 0.500 liters. So X equals 0.075 moles. So now what I have to do is I have to do a little bit of stoich to get myself out of moles and into grams. So I know 1 mole of NaCl is going to have a molar mass of 58.443 grams. How I got this number was by adding 1 Na and 1 Cl together from the periodic table. So now if I want to figure out how many grams that is, I just multiply this by 58.443. That gets you 4.38, which would round to 4.3, 4.4, depending on how well you round it. So that's how you do 21. 22 says 25 milliliter solution of 2 molar HCl is diluted to a new volume of 1. The concentration of the new solution is. Because I see this word diluted, that means we're going to use a new equation. We're going to use our dilution equation, which is M1V1 equals M2V2. So M1V1 means the stock side, it's the concentrated side you're starting with. The M2V2 means your diluted side. So from this problem, I would go ahead and I'd put my molarity, because big M means molarity. So I'd put 12.0 in for my M1. And I can keep it in milliliters this time. So I put 25.0 milliliters in for my V1. I'm going to solve for M2 because it's asking me for concentration. And my V2 is 1.00 liter. Now here's the tricky part. Because I'm liters in one and milliliters in the other, I have to convert one of them into the right unit. So in this case, I'm just going to divide this by 1,000 to go ahead and get me to a liter. So my problem, I would do 12 times 0.025, and I would divide by a liter, which is 1, and I would get 0.3. So that means my new volume is 0.300 molar. 23 says what volume of 1.00 molar CaOH is required to neutralize 100 milliliters of 0.200 molar HCl. This actually is from your titration equation. This should be part of chapter 16. I put that in the wrong spot, so I apologize. So let's run through that one. This is actually not a chapter 15 problem. This would be a chapter 16 problem. This would be a titration equation. So this time what we're going to do is we're going to use MABABA. So I'm going to change pen color. So let's go purple. Oh, not take this. So this is actually chapter 16. My fault. Wrong spot. So we're going to use MABABA. So MABABA. So remember, Ma is molarity of the acid. Va is volume of the acid. Ba is your mole ratio of base over acid. Mub is molarity of your base, and Vb is volume of your base. So the first thing we have to do is we've got to write a chemical equation. So I've got CaOH, which is my base, and I know it's my base because it has OH in it. It's neutralizing HCl. I know this is my acid because it's got an H in front, and we're going to do double replacement. So my H is going to go with my OH to make water, and my Ca is going to go with my Cl. Now I know my compound is CaCl2 because Ca is plus 2, Cl is minus 1, so I need 2 of them to make my total charge 0. So I can go back and balance by putting a 2 here and a 2 here. So I read through my equation. I'm trying to find my molarity of my acid stuff. So I know HCl is my acid. It's 0.2 molar. So in my Ma, I'm going to put 0.200 molar. Volume of my acid, it tells me it's 100 mils. And now my mole ratio is my base over my acid. So my base has no coefficient, so I'm going to put the number 1 in front of it. My acid has a 2, so I'm going to put a 2 on the bottom. So the mole ratio just comes from the coefficients in the balanced equation. I'm going to look for molarity of my base. It tells me it's 0.100, and I'm solving for the volume of my base. So in my calculator, I would do it's 0.2, so there's no decimal place. I would do 0.2 times 100 times 1/2, and then I would divide it by 0.1. And that gets me, I don't think I did that right in my calculator. Let's try that again. 0.2 times 100 times 0.5 divided by 0.1. Nope, no, that's right. So it would need 100 milliliters of my CaOH2. And on your test tomorrow, just so you know, there wouldn't be an acid question in the middle of the solution stuff. It would be in its own chapter, so I'm sorry about that. All right, number 24 says, how much potassium iodide in grams should be added to water to produce 2.5 liters of a solution with a concentration of 3.5 molar? Now, because we see that molarity guy again, we're going to go back to that molarity equation. So we're going to go back to our big M equals moles over liter. But this time, because it's asking for grams, we're going to have to do a little bit of math once we get to moles. So the first thing I'm going to do is I'm going to solve for moles. So I've got my 0.35 molar is equal to X over 2.5. So if I solve for X, it's going to give me moles, which is 0.875 moles. So now I'm going to do here is I'm going to do molar mass. I don't have a periodic table handy because I left it at school, so I'm not actually going to finish this problem because I don't know the mass of iodine off the top of my head. So what I would have to do is I'd have to look up the mass of potassium, the mass of iodine, and add those numbers together to get this guy on top. So I hope that that's helped you kind of understand how to figure out what equation to use in your solution section tomorrow. The next question I got is, can you do number 3 on the first page? Now, I'm not really certain what number 3, because in the review packet, number 3 is gas law stuff. So that's what I'm going to copy in. I'm not certain this is the right question. So if you're the person that typed this in, and you're watching this either now or later, if you would, email me if this is the question you're asking about. So this is actually an acid-base question, or sorry, not an acid-base question. I'm looking ahead. This is actually a gas law question. So this one's talking about pressure and volume. So it says the sample of a gas is the temperature of a sample of a gas is decreased. So we're taking the temperature and we're dropping it. The volume of the gas will. So if we think about what's happening, we're taking our temperature and we're dropping it. So that means the kinetic energy of our particles is dropping. So if they were in a super, super big balloon and they were moving crazy, 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 crazy fast in here and hitting the sides of the balloon and making it inflate, we're now cooling it down. So in that same big balloon, our molecules now are only kind of moving slow. So because they're hitting and moving slow, that means the pressure in our balloon is actually dropping. So we're not going to be able to fill that space anymore. So the outside air is going to push in on all the sides, and it's going to decrease the volume of that balloon. So if my temperature goes down, my volume will also go down because our particles are no longer moving fast enough to fill the space they were in. All right. So we're about halfway through. We've done 3 of the 3 chapters that we are going to go through this chapter. So if you are someone who is still watching, thanks for hanging with me. If you're watching this at a later date, thanks for viewing later. So we're going to head into some acid-base stuff right now. So for acid-base stuff, you do not get anything. So people always are like, oh, I get the square of awesomeness. You do not get the square of awesomeness. So make sure your square of awesomeness is on that cheat sheet. That's the number one thing that people are like so mad about. Oh, no, I thought I was going to get it. Sorry, you didn't. Nope, not so much. So let's continue on now with acid-base. Share. Alrighty, room. So how can you tell if it's acidic or basic after solving an equation problem? Now, I'm guessing that this is referring to like a pH problem. That would be my guess. So a couple of different ways you can tell. I always like to just go ahead and turn everything into pH. I think it's a lot easier to remember just one thing than a bunch, but I'll tell you all the ways you can remember it. So the general rule of thumb is we know that pH of 7 is neutral. So if your pH is less than the number 7, that means you're acidic. If your pH is greater than 7, that means you're basic. And if your pH is exactly 7, that means you're neutral. So that's one way you can figure it out, is just kick it into pH. If it's less than 7, it's acidic. If it's more than 7, it's basic. If we think about H plus and OH minus, if your H plus number is bigger than your OH minus number, that is also going to mean acidic, because we know that H plus means acid. So if this number is bigger, that means you have to have something that's an acid. If your OH minus is bigger than your H plus, oh, that's not bracket. That would mean you're basic, because we know OH minus means basic. And then if your H plus and your OH minus are exactly the same as each other, then you're neutral. So that's how you can tell if something is acidic, basic, or neutral. I like to just solve for pH using your square of awesomeness and then just look at the number, because I think it's the easiest way to do it. But whatever way you want to do it, go ahead. Next question. What does it mean when a strong or weak acid ionizes? What that word ionizes means is to break apart into ions. Oops. I'm trying to do too many things at once. All right, what that word ionizes means is to break apart into ions. So if it talks about a strong or weak acid ionizing, a strong acid is going to fully break apart. So if it was in a beaker, so let's say our strong acid here is HA. So what that means is if we were to have a beaker of it in water, we would have a whole bunch of H pluses and a whole bunch of H minuses because it's fully breaking apart. So we're going to have a really, really, really acidic pH. If we have a weak acid, we'll call him HB. They don't really ionize that well. This is like the weak girlfriend who can't be without her boyfriend. So you're going to have a whole bunch of HB molecules stuck to each other and only a little bit of H plus and a little bit of B minus. So that's what we mean when we say a strong or weak acid ionizes. A strong acid is going to fully ionize and make a really, really acidic pH, where a weak acid is only going to slightly ionize and make a slightly acidic pH. So that's what we mean when something ionizes. Last question is about buffer systems. This was something that was really tough for you guys, so I'm glad that someone asked about buffer systems. So they said, why is H2O not a suitable buffer system? It's not a strong acid, so why? So that's great that you understand that you cannot have strong acids in buffers. So that's the first thing, is you cannot have anything strong. So great catch on that. The thing that you have to do is you have to make sure that they're a conjugate acid-base pair. So a buffer is going to have a weak acid. I'm going to write this a lot neater. It must be a weak acid and its conjugate base. So remember, when we think about conjugate bases, you can only take one H off at a time. So if I think about H2O and O2 minus, for me to go from H2O to O2 minus, I would have to lose two H's, which is too many because the conjugate base can only have lost one H. So a way to show you that a little bit more clearly would be like looking at H2SO4. No, let's not do that one. Let's do H2S because it's a weak acid. So if I want to know if it's a buffer, if I have S2 minus, it's not a buffer because it's lost too many H's. It's lost two H's. If it's HS with a minus, then yes, it could be a buffer because it's only lost one H. So the definition of a buffer is it must have a weak acid, which H2S is, and its conjugate base, which means it's only lost one H. So this would be our buffer system. This would not work. So that's why this guy would not be a buffer. It's simply lost too many H's. All right, on to chapter 17. Review question 37. When heat is added to NBR, why won't it shift right? So let's go ahead and let's pull in review question 37. It's using the Le Chatelier's principle, which of the following would shift the reaction to the right? So this one's asking about sorry, my dog's trying to eat my gum. That was in my school bag, not my mouth. Just want to qualify. All right, so review question 37 says, when heat is added, why won't it shift right? So if we look at D, it says we're adding heat. If we look at where this reaction is, heat is written on the product side, meaning that it's exothermic. So what that means is when I add heat, I am increasing the amount of heat that's on this side of the reaction, which would force it to go forward more to the left. So heat will only make a reaction come to the right if it's endothermic. So you want to think of heat just like concentration. Because heat is a product, by heating up my reaction, I'm making the product side bigger. So my reaction has to go the opposite direction. So that's why it will not shift it to the right. The next question I got was about the law of chemical equilibria and what KEQ has to do with it. The law of chemical equilibrium and KEQ are essentially saying the same thing. What the law of chemical equilibrium basically says is that if you have a reversible reaction, you can figure out if it's product or reactant favored by doing some math to figure out what you have more of at equilibrium. So the law of chemical equilibrium is just telling you how to write a KEQ. So they're both kind of saying the same thing. So just to show you guys how we write a KEQ equation, in case you want a quick review of that. Oh my God, Admire. Actually, let's do this. We'll do 2NH3 goes to 2H2 plus 2N2. That's not balanced. This should be a 3. All right. So if I'm writing a KEQ, these are all gases. So remember, we do not include solids or liquids in KEQ, and you always put the products over the reactants. Your coefficients become the power that you raise your math to. So if I want to write the KEQ for this, I'm going to put my products on top. So I'd have H2 to the third times N2 to the second all over NH3 squared. So remember, if your KEQ is bigger than 1, that means that you are product favored. If your KEQ is less than 1, it means you're reactant favored. Because in order for me to have a number bigger than 1, my top number needs to be bigger, which would mean I'd have more products at equilibrium. In order for my KEQ to be less than 1, it means it would have to be reactant favored, because I'd have to have more reactants present at equilibrium. All right, on to the last couple of questions. Chapter 18, what is the importance of shorthand? Will we be tested on this? This question cracks me up. It was not an emotions exam covering test that we just took. I agree with you, it wasn't, because I forgot to put it on there. And no, you will not need to know this on the final, so I'm not going to waste any time. No shorthand on the final. Smiley face for you guys. All right. And the last question is, why is it that the further away two metals are from each other, the better the battery? This all comes down to electronegativity and what metals want to do when they have electrons. So if we think about the activity series, I just know the activity series I give you guys, we've got lithium on the top, we've got Ag or Au on the bottom, and there are a whole bunch of metals in between. So lithium is at the top, which means it's really reactive. So it wants to lose electrons because it has a low electron love. It's got a really low electronegativity. This Au really wants to gain electrons because he has a high electron love. So when I put something that really, really wants to lose electrons with something that really, really wants to gain electrons in a battery, what's going to happen? Here's my little bad battery drawing. Salt bridge, wire. So if this is my lithium, that would be my anode, and this is my gold. This would be a really expensive battery. That's my cathode. Because lithium really, really wants to lose electrons, you're going to have electrons being made like crazy. And so you're going to have a whole bunch of electrons being lost and coming into the wire. Because the gold really, really wants to gain electrons, they're going to be sucking these electrons in really, really, really fast, bringing them closer to this electrode so that we can get the electrons gained really fast. So this guy is going to lose electrons really quickly, and this guy's going to gain electrons really quickly. So we have a whole ton of electrons just whipping through this wire. And that's why you would get a battery with a really high voltage. Conversely, if we were to make a battery that was silver and gold, because they're right next to each other, so if I draw another really bad battery, salt bridge, wire, so here's my silver, here's my gold, sure, this guy would gain electrons, and sure, this guy would lose electrons because silver's above the gold. But because they're both right next to each other, it means their electronegativities are almost the same. So this guy's going to lose electrons, but it's going to be at a much slower rate than our other battery, because these have a really big difference in electronegativity. So this guy really wants to pump them out, and this guy really wants to gain them, where these guys are really close in electronegativity. So he doesn't really want to lose them, but he will, because he's just a little bit less electronegative than the gold. So it's just going to be a much slower transfer of electrons than the guys that are further apart. And I believe that is our last question. So I hope that you found this helpful. I hope that you were able to get your questions answered that you had before final exams. I look forward to seeing you all on your final exam day. And I just wish you guys the best of luck. It's been a great year, and make sure you come back and get your high fives next year on High Five Friday. But don't forget that textbook. It's $80, and I don't want you guys to get charged that. So have a great night, and I will see you guys all over the next couple of days. See ya.